Okay, so we restart the lecture where we left it last. This was this slide and talked about the various hypothalamic nuclei and their proximity to the hypophyseal, hypothalamo-hypophyseal tracts, posterior pituitary and hypophyseal vessels of the anterior pituitary. We will pick up the next slide from here. So this now basically shows details of various nuclei, which, as you can see, are numerous, but they're basically divided into anterior and posterior nuclei. There are, of course, these are anatomical details, and you will be studying this when you will study neuroanatomy, specifically of the hypothalamus. But however, as far as physiology is concerned, there is one consideration that as you go higher in the brain, and as you go to more complex functions of the brain, you find that, at times frustratingly, that many of the details are missing. We simply don't know how things work. We just know that they work. So, for example, a thought is produced in the frontal cortex. We still don't know details about how this thought is physically generated. We know it's generated, but we don't know how it's generated. So many of the stuff that you will see in your textbook regarding hypothalamic functions, it will have sentences like it's postulated, it is thought to be doing this, and estimations of this sort. So there are unknowns with some knowns when we rise up in the brain and deal with more complex issues. So hypothalamus is one of those examples. So you see a lot of nuclei, which basically are divided mainly into, as far as this lecture is concerned, anterior, posterior nuclei. Now, I would like you to remember three sets or three combination of nuclei. So basically, my lecture will not emphasize on each one of the nucleus, and because in physiology, it's the function of this hypothalamus that we're concerned with, and the function, each function depends on a multiple combination of various nuclei. So there are three combinations that we want to focus on. One is the anterior hypothalamic area and preoptic nucleus. So this is the anterior hypothalamic area right here. This. And the combination is with preoptic nucleus. So these are the two preoptic nuclei. This together with the anterior hypothalamic area. This is one combination. We'll be coming back to this in the three integrated examples that we'll be studying. Second is, it's not on this diagram, but this is a Guyton diagram. It shows of course you will appreciate that this is a lateral view of the whole thing, while it does not show the anterior aspect. It cannot on this design. You want to see the anterior of the hypothalamus. This is the view. This is the front view. You see arcuate nucleus. You see periventricular. This is the ventricle. So periventricular nucleus, which you can see is in close association with output. And you see paraventricular on both sides, of course, paraventricular. And then you see the lateral hypothalamic area. So basically, this is a combination arcuate nucleus, peri and paraventricular nuclei, and lateral hypothalamic. So these are the two that I mentioned. Once again, in this slide, we talked about anterior hypothalamic area and preoptic nuclei. Then in here, we talked about arcuate, periventricular, paraventricular, and lateral hypothalamic area. So the third is not shown in either. It's basically somewhere, somewhere in this area, right? It's called the SCN, the rather in this area, SCN, the suprachiasmatic nucleus. Suprachiasmatic nucleus is very, very important. We will study this. So these are the three nuclei, the three sets of nuclei, three combinations that I would like you to remember from the physiological point of view. However, from the anatomical point of view, you will be required to remember the whole thing. Right. So now we move on to the functions of the hypothalamus. And because hypothalamus is the center of basically what's happening in the limbic system. That's why we basically, and most of the stuff is unknown anyway. What is known mostly is about the hypothalamus. That's why whenever you will study limbic system, you will focus on hypothalamus for these reasons. So once again, uh, this is a rather long list of functions of the hypothalamus. Let me just give you a view. This is the anterior nuclei. These are the anterior nuclei, and their functions is given below them, below the names. Then you have the posterior nuclei. So let's see. You will notice that the entire slide is in black except this one entry here, which is red. Let me give you a concept here quickly. So basically, the way Guyton has written it, he has discussed hypothalamic functions uh, in its totality. So it discusses the vegetative functions versus the behavioral functions. Vegetative functions, you can imagine, are, say, bladder contraction. It has nothing to do with behavior, right? While we are discussing behavior, because we are discussing limbic system. So this is an addition that he discusses vegetative functions here as well, because, well, while we are at it, we are discussing area. He gives the list, the holistic list, where he mentions everything. However, bladder contraction, as you know, will be discussed in renal physiology. Heart rate and blood pressure, you have already read it in cardiovascular physiology. So all of these, the one in the black, they basically are vegetative or non-behavioral. However, the one which is given in red is the behavioral function. There's something to note. Then we look at the posterior one. Here you see these, and remember, if you remember, we talked about arcuate and periventricular nucleus, something to remember. There are some neuroendocrine action here, and which is vegetative, and fear and punishment reactions, which is behavioral. You have this, and you see a lot of red stuff now on the slide. Also, most of the posterior hypothalamic nuclei deal with the behavioral functions of the hypothalamus. All of these. For example, what is satiety? It's the feeling of fullness when you've had a meal and you don't want to eat any further. Um, so you can imagine this nucleus basically, if stimulated, it causes the sensation of satiety, decrease eating, and tranquility. So after you've had a meal, you're all right, you're relaxed. Okay. However, when you're thirsty and hungry, you are upset. Of course, I wouldn't say that you would go into a rage reaction, but remember, these things are derived by animal experiments where they stimulate or hyperstimulate various portions of the brain to elicit the reaction so that it's studied properly and documented. So, the lateral area of the hypothalamus, when it's stimulated too much, uh, the upset, the upsetting sensation of thirst and hunger can turn into rage and even fighting. And you will see that hunger and rage they constantly, consistently feature together. Now coming to the three integrated examples. Now remember, till now we have discussed the anatomical positions of the hypothalamus, the anterior and the posterior one, and we mentioned the very in brief lines the functions of each of these nuclei, and we kept on focusing on the three combinations of nuclei which are important, which are discussed in your textbooks, and you will see why they are so important. One, the one, if you remember, the arcuate nucleus, periventricular, paraventricular, and lateral hypothalamic area combination. It is basically dealing with feeding behavior. And now this is an interesting term for you, feeding behavior. It's not just feeding, there's a behavior behind feeding. And you can see that this varies from person to person. The way we feed ourselves on a daily basis, not just daily, not just meal to meal, but in the long term. Some people tend to eat less, some people tend to eat more, some people tend to eat small meals throughout the day. So they may end up feeding themselves 4, 5, 6 times. And some people restrict themselves to the classical 3 times a day. And then this then translates into a pattern of behavior. So for example, the people who are accustomed to having 3 meals in a day, if you try to give them more than that, that will be an uncomfortable experience for them because that's their behavior, 3 meals a day. So behind that, you have all that machinery which we will look at in a moment. The second is anterior and preoptic nucleus, anterior hypothalamic area and preoptic nucleus, as we mentioned. So we will talk about how it affects the gonads and the sexual activity in humans. Third is the suprachiasmatic nucleus, SCN, and here we will talk about how this is the master gland, or the master clock rather, of the hypothalamus, the internal biological clock. We will study some pretty interesting things under this head. Okay, starting from the top, let's look at hypothalamus and how it sort of controls the feeding behavior. So, this is an interesting point here. Food intake, what you eat, and out of that, what you spend in terms of energy. So food is translated into energy, and then either you store it or expend it. And reproductive function, they all go together. So it's the food and the mating behavior, they're congruent in the hypothalamus. They go together. If an animal is empty stomach, it is unlikely to mate, and vice versa. So hypothalamus basically regulates, as we will see in a bit, caloric intake, its use, storage. And in that way, it basically controls, regulates a set point of body weight. Our body weight as adults, not as growing children, as adults, uh, most of us basically have set points, constant set points of body weight. It doesn't fluctuate horrendously. Okay, in Ramadan, uh, we tend to shed some kilos, pounds, uh, or gain, depending on how you fast and what are your activities. But generally speaking, if your exercise profile is relatively constant, your feeding behavior is relatively constant, your body weight will not fluctuate horrendously, very significant. So this is basically the function, key function, one of the key functions of hypothalamus. How does it do it? This is how it's done. For reference, I have copied that diagram that we looked at for the location of arcuate nucleus, periventricular, paraventricular, and lateral hypothalamus, because these are all mentioned here. Okay, we'll start from the bottom and see this is they've shown the arcuate nucleus. Okay, arcuate nucleus has uh, two components, two areas where two peptides are released. One is this area, and it releases POMC. POMC stands for propriomelanocortin peptide, and another area which releases NPY, which is neuropeptide Y. When you read the supplementary material that I will be posting on WhatsApp, you will get some additional information about these two peptides. So these are the two key components of arcuate nucleus which are involved in feeding behavior. When we say that arcuate nucleus is basically the, let's say, the gatekeeper of of the various stimuli that come from the body, and then integrates them, these stimuli, the information that it receives, and then gives it off to higher other areas of the hypothalamus, um, which then project it to other, even more higher or different CNS areas. And eventually, this whole circuitry, which is this direction is like this, from bottom to top, they determine whether you will feed and or you will expend your energy. Okay, so this is the summary. Let's go in a bit of detail. Remember, these are not set in stone. Many of these things are still under consideration in research. So this area here, which secretes this POMC, basically, what's the function of POMC? When POMC, this area which secretes POMC is stimulated and POMC is released, it basically decreases food intake. So you can say that it decreases appetite. Okay. And at the same time, it increases energy expenditure. So it's released in a situation where you have abundance of substrate. You are feeding or have just fed, taken a meal. Okay. So somebody needs to tell the hypothalamus to tell the rest of the CNS, which deals in feeding behavior, to stop, because you've just had your meal, right? And you are now free to expend your energy because you've had your meal and you're good to go. So this is how POMC fits this bigger picture. Okay. Once again, it decreases food intake. So you can say that I won't use the word satiety center because these are old terms now. More simplistic view of something which is quite complex actually. So this POMC basically heralds the sensation of satiety, which is decreased food intake, and more energy is now signaled to the organism uh, to expend. Uh, Neuropeptide Y is the opposite of POMC. So basically, when it is the area that it is contained in, is activated and it's released, it basically increases food intake and decreases energy expenditure. These are opposites. Uh, Before I talk a bit about these three things here, let me just give you the circuit, how it's done. So stuff which stimulates POMC inhibits and the neuropeptide Y, which is understandable. And then eventually, uh, some stuff is inhibiting the neuropeptide Y, some stuff is stimulating, but overall, this inhibits POMC. Okay. So you can say that the POMC is the main signaling peptide, and it's under regulation of stimulatory stimuli from the body, and then eventually inhibition from its fellow peptide, the NPY, which in turn is under influence of various stuff from the body. I hope it's not too complicated. Once again, I will direct you to the additional supplementary material that I have forwarded, or I will be forwarding it with this video. And it actually mentions the number of the slide. Of this slide, I think it's 37, if I'm not wrong. And it actually mentions hypothalamus and feeding behavior. So you need to just go through that and you'll understand in depth. Once again, as I usually do, remind you that no amount of lecturing or summaries or reviews is a replacement for your own personal reading of details from a standard textbook. Okay. So very briefly, leptin is a hormone which your adipose tissue releases when there is abundance. When you are having your food, or when you've had your food, leptin is released. It tells this area to release POMC, which eventually inhibits further food intake and puts you into the energy expenditure mode. Coming to this side of things, ghrelin is a hormone which you release on empty stomach. And very quickly, if you see that it stimulates the release of neuropeptide Y, and we know that neuropeptide Y will stimulate food intake and decrease energy expenditure. So ghrelin, as I just said, is released empty stomach. It is released before you take a meal, before the stomach is full. As the stomach starts to get full with food, ghrelin starts to decrease. So this is ghrelin effect on arcuate nucleus of hypothalamus, and then finally insulin from the pancreas. It inhibits neuropeptide Y. Of course, if you have neuropeptide Y which increases food intake and you have insulin there, insulin would inhibit it, because insulin again is a hormone of quote unquote abundance. It is released when you have had food. So when it's increased in the blood, it should inhibit things which promote food intake, which is NPY in this case. So insulin basically inhibits. An interesting cross-talk between insulin and leptin is that insulin also stimulates leptin, something which is interesting to note. Right, so I think we have learned this enough. We can now proceed to the next slide. Right. So not any, there are some interesting bits here. There's talk about puberty. There's talk about puberty and sexually dimorphic nucleus, which is interesting. So basically, I spoke to you about the second combo that we'll be talking about, the anterior and preoptic hypothalamic areas. These are the sites of GnRH production, production secretion, which then determines sexual behavior. So at puberty, there is what scientists have found that somehow, and again, it's not known exactly how, at puberty, some stuff, some signal from somewhere comes to this preoptic area, the neurons in it, and they suddenly start to increase secretion of GnRH, gonadotropin releasing hormone, which then stimulates the release of sex hormones from the anterior pituitary, as you know. So this at puberty is this whole thing is a hypothalamic function, basically. That's why it's mentioned here. Secondly, which is very, very interesting, is during the fetal life, the brain, it's neutral. But this part, the preoptic nucleus and the anterior hypothalamic areas, these parts, under the influence of, say, the testosterone, during fetal area, if it's a male baby, they change. They change. And they change in a way that later on in life, they will direct the GnRH to release testosterone, not estrogens, in the male example. And if the fetus is female, then it won't have testosterone in the system. So these areas will not be exposed to testosterone in this case. And in that case, the GnRH will eventually stimulate the estrogen formation from the pituitary, which basically eventually results in sexual dimorphism. It basically means that male and female body form and shape are different. And you know how different they are. That's called sexual dimorphism. And this nucleus is nicknamed as the SDN, sexually dimorphic nucleus, because it is this area which in the fetal life is exposed to androgens. If it's exposed to androgens, it will eventually direct the formation of testes and all the male sexual organs and body and shape of the male. And if it's not, then conversely, it will lead to formation of ovaries and extra female genitalia and the size and form of the female. So that's the second integrative scenario that we've discussed. The third, and by no means the least, is the biological clock. You must have read it in your high school years, that we have a biological clock, which is different from the clock that is in your room right now. It's an internal clock. And today, I've learned that it basically is the hypothalamus that contains and regulates the biological clock. And what in hypothalamus? It's this nucleus, suprachiasmatic, SCN. This serves as the brain's biological clock. Right. So as you know, we basically on a daily basis are in a rhythm. And we defined what's the difference between rhythm and cycle. Rhythm is more of a change on a daily basis, while cycle is more number of weeks or months. So this is a rhythm that we're talking about, sleep, wake cycle, okay? And they have mentioned 4 things. There are many other things which are hormonal in nature and other functions of the CNS which follow this pattern, these rhythms. So here, alertness, as you can see, the time of hours is here. So 6 hours from 0, then 12, then 18. So this is around between 12 and 18 hours is basically Zohar time, Zohar prayer time. This is where alertness is peaking. This is an interesting thing, right? And afterwards, as you go into the evening towards the night, the awakeness goes down. And then again, from the morning, early morning, you start, and there's an incremental pattern to this alertness. Temperature is interesting. There's about 1 degree difference in temperature during the day. Growth hormone, it peaks during sleep. You will study this in endocrinology. While during the day, it sort of is in a trough. Cortisol, you need it when you wake up. So right in the wee hours of Fajr time, it's peaking, and as the day progresses, it sort of goes into these fluctuations depending, and it also, of course, depends on the kind of activity that you are in, emotion and other things. So basically, all of this is just an example of the biological flaw. Something is controlling these behaviors, these fluctuations here, and that something is basically the SC. I found, I believe this is in the latest edition of Guyton, this excellent diagram that basically shows where the SCN is. It's right conveniently right behind the eye. It's connected actually with the eye via the retino-hypothalamic tract, which gives it, no surprises here, which gives it basically a sense of whether it's day or night through the amount of light that is entering the eye. So, as you can imagine, the rhythm that it then controls, whether it's the sleep wake cycle, mood, appetite, or various ANS system related functions, various neuroendocrine related functions, and the feeding behavior. All of this is basically dependent on the day-night cycle and the amount of light that enters the eye, stimulates the retina here, and then via this tract is delivered to the SCN, which then determines if it's the day, then it will basically adjust all of these smaller clocks in the CNS accordingly, which very nicely done here in Guyton once again, which then directs the, let's say, the organ clocks, okay, subsequently to the orders of the SCN. So SCN controls CNS clocks, which then affect or influence or regulate the organ clocks. So during the day, you have a certain cardiovascular profile, your heart rate, your cardiac output is of a certain, is at a certain level. While when you sleep, you don't need that level of cardiovascular activity. So it changes. Same is the case with kidney. How kidney functions during the day is different when you are asleep. And then feeding behavior, we've already talked about it. It depends. You can train yourself to be more hungry during the breakfast and the lunches, and less hungry during the dinners. And this, by the way, is a very healthy habit. Everyone should adopt it. So this is the biological clock overview. Once again, I refer you to the supplemental material to have a good read of it. Guyton actually has mentioned that in 2017, the Nobel Prize of Medicine and Physiology from the Karolinska Institute, Sweden, that's where it's announced, was given to a couple of blokes who worked on biological clocks actually. It's not that simple, but in a headline sort of a way, that's how it is. They looked at some molecular biological clocks, the molecular signal peptides related to biological clocks. The point here is it's still a very relevant and a very hot topic in research. Okay. This again, I mentioned in the initial slides, the reward and punishment areas that you'll be reading it a lot in the latter part of the chapter in Guyton. So there are reward centers and punishment centers. Again, these are based on experiments on mice and other animals. Uh, their brain would be opened up, and electrodes would be attached to various components, various parts of the hypothalamus. And then these electrodes would be connected to paddles, that if they were to move that paddle, that electrode would stimulate the corresponding part of the hypothalamus. And then the animal would experience something. So basically, they divided it into two main areas. One is reward areas, and the other is punishment areas. So they saw that the certain areas, the animal would, as I mentioned earlier as well, the animal would prefer to press those electrodes that fell in the reward centers, as opposed to the punishment quote unquote centers. Where are the reward centers? In the human brain, these are postulated to contain the reward centers. You just have to really remember this. Nothing fancy in its explanation. And the punishment center are postulated to be in these areas. So that's reward and punishment. Uh, this is an interesting point I mentioned in Guyton. That if you stimulate punishment centers enough, they have this ability, characteristics rather, to overwrite the pleasure centers. If you stimulate punishment centers strongly enough, they can actually put the pleasure centers out of business. So all you feel is punishment. Uh, this has huge implications in the way we behave in certain situations and do not behave similarly in other situations. It has big implications in the way we learn certain things, and we are unable to learn other things. Uh, Punishment and fear, well, unfortunately, it takes precedence over pleasure and reward, as this part of the slide mentions. Um, and it has implication, as I mentioned, in learning and memory. So uh, the things that you find valuable to your person or to your career or to your family, you tend to remember them and you tend to ignore the rest of the stuff, right? I'm sure you were taught in sensory systems of the sensory stimuli. There are lots of sensory stimuli. You putting on clothes in the morning is a sensory stimulus. Is it something that you need to remember? No. But if the shirt had a little bee in it, which stung you this fine morning, which was otherwise fine, but before the sting, then you would certainly remember to look inside the shirt before wearing it for probably the rest of your life. This is how things are sorted. What would be remembered and what can be ignored, and you'll be surprised that 99% of sensory stuff, sensory information that goes up the ladder, ascending sensory tracts to the CNS, is rejected, and about 1% is remembered. Okay, so anything which does not stimulate a reward center or a punishment center is really unlikely or almost certainly likely to be ignored and be part of that 99% rejected stuff. Stuff which stimulates the reward and punishment center, that is learned and put in memory. How is it learned? It's learned by reinforcement. So there are areas of the limbic system, mainly the hippocampus uh, and the amygdala, which keep on repeating things. Basically, the hippocampus, it keeps on repeating it. It keeps on, let's say, revising the reward or punishment sensory stimulus. So much so that eventually, through this repeating and revising, it's the technical word is reinforcement, it's committed to memory, right? And the 99% of the stuff which is rejected is habituation. So we are used to rejecting the putting on the shirt without the B, as the example that I quote, and the rest of the things which we tend to ignore. We don't commit it to memory. And remember, if we start committing to memory everything that goes up the ladder, as in sensory stimulus, sensory information, we'll run out of space, just like computer. Okay. So before we discuss this, we will take a break in this presentation.